Hello everyone, my name is Dietrich Geisler, and today I will be telling you about geometry types and how they apply to graphics programming. This is joint work with Irene Yoon from University of Pennsylvania, Aditi Kabra from Carnegie Mellon University, and Horace, Yinnon Sanders, and Adrian Sampson from Cornell University. Graphics programming is a large and expanding field involving everything from computer animation to video games to computer simulation and modeling. Unfortunately, graphics programming is a relatively underdeveloped area that has relatively underdeveloped languages that contribute to the challenges behind graphics programming. See, graphics programming is a notoriously difficult area to get started in. In particular, graphics programming introduces new kinds of domain-specific bugs. When I went to go write some simple graphics programs, say a lighting model on the left and a shadow on the right, what I instead got was something that looked like this. In each of these examples, it's clear that something went wrong, but figuring out what went wrong is a challenge. The correctness of a graphics program is, in some sense, in the eye of the beholder. So figuring out what went wrong in these images comes down to looking at the image long enough and maybe looking through some code and trying to guess at what the problem might be. What we propose is a solution to a particular kind of bug that shows up in graphics programming, namely a geometry bug. We propose that geometry bugs are subtle, pervasive, and hard to catch, and that they can be caught and found by something called a geometry type. Not only can geometry types rule them out, however, but they can also generate correct by construction transformation code. Throughout this talk, we will be using a simple lighting model as a running example. What do I mean by a lighting model? It is just where you take a three-dimensional mesh or model, like this alligator shown here, and try and illuminate it using a light source so that areas facing towards the light are brighter than areas facing away from the light, creating the illusion of 3D. What this looks like mathematically is that what we're trying to do is calculate the light direction and take the angle between the light direction and what is called the fragment normal. The fragment normal is simply a vector that points directly away from each face of the Gator or the model's current vertex that we are working with. Given this angle calculation, we can then simply say that the color of that face is just equal to that angle. So a very small angle will have a very bright color, and a very large angle will have a very dark color. That is, it's facing away from the light. Specifically, what this looks like is we calculate the light direction by taking the normalization of the light position minus the fragment position, and then we compute the color by taking the max of the dot product, or the angle between light direction and fragment normal, and then maxing that with 0. The reason we max with 0 is to ignore things that are facing away and make sure that those come out completely dark. The way we're actually going to implement this is very similar to the mathematical model shown below. Specifically, we're going to introduce a function called Diffuse that takes in a light position, a fragment position, and a fragment normal, and calculates a light direction by taking the normalization, and finally returns the dot product max with 0. Unfortunately, this code produces the Buggy Output shown below, because there's actually a subtle bug going on already in the simple implementation that just took a mathematical model and applied it. So how in the world can this happen? The problem is that light position and fragment position are different flavors of vectors in real graphics code. While the mathematical model is what we wanted, the actual implementation has this subtle issue where light position and fragment position are different kinds of things. And it's important to note that this is in no way shown in the code above. This is pretty standard GLSL, a common graphics programming language, code. And what we can see is that light position, fragment position, and fragment normal all just float through. There's no special modifier on them that tells you what flavor of vector they are, which is apparently a thing you have to know. Otherwise, you get wrong output. So you just have to have this intuitive understanding of what it means for vectors to have different flavors, or as we will see, frames of reference, and be able to understand this just by looking at a tutorial and looking through your code and figuring out where the issue it might be. There's no indication that this is a wrong output. And unfortunately, fixing this output is fairly complicated. As we can see here, we have to introduce a U model matrix which is an entirely new construction that didn't show up previously. And then we have to multiply it by vec4 of frag position, and the same thing with fragment normal, and then there's like a 1 and a 0 there, a 1 and a 0 respectively, and then we have to add this vec3 function, and it's unclear exactly what this is doing, but somehow this is going to fix the problem. So I'm going to walk you through the rest of the talk exactly, first of all, how this fixes the problem, and a much nicer way to do it in the form of our novel geometry type. So to just explain the components of a geometry type, what a geometry type actually is before we dive into the details of this function, is we take a simple type, say a float3, and we extend that type to instead describe the geometry components or the geometry description that makes up that type, that makes up the actual vector being represented. Specifically, we want to introduce a coordinate scheme, a geometric object, and a reference frame. I will briefly describe each of these components, and then we will see how those interact with the code that we saw previously. First of all, a reference frame is essentially the orientation and position that each vector is oriented from. So there might be a world reference frame, which is where things are relative to each other, and then there's the model reference frame, which is the perspective of the alligator. There's the coordinate scheme, which is the numerical representation of each vector. So for example, Cartesian or polar coordinates are fairly commonly known coordinate schemes. And then finally, there's the geometric object, the actual thing being operated on. Things like points, vectors, and directions are all examples of geometric objects. Going back to our code from earlier, we want to figure out what's going wrong with this light position minus fragment position operation. So what's specifically going wrong is that the light position and the fragment position are in different reference frames. Again, different flavors of vectors. Specifically, the fragment position is originally represented in model space. That is the perspective, in the model reference frame, that is the perspective of the alligator. Instead, however, we can represent that same vector with the world position vector, which is the same point represented instead from the perspective of the world reference frame. This is important because light position is originally represented in the world reference frame, as we can see here. So we need some way to transform fragment position to world position so that we can have the same representation form or same flavor between world position and light position and actually do our subtraction. What this looks like in code is we need to introduce the U model matrix. See, this matrix is a transformation matrix that goes from model to world, and when you multiply U model times fragment position, you get something in world, a world position vector. In code, what this is going to look like, the first thing that we're going to do is we're going to introduce this idea of flavors, where this is our first step into a geometry type. We're going to introduce world and model for light position and fragment position, and then finally we have auto, which is just an inference. It's going to infer the type of what light direction is. In this case, what we will actually get is an error because light position and fragment position are in different reference frames, so we can't apply a subtraction between them. However, by introducing the world position vector, then we can have the correct types and the flavors all work out. But we still have to calculate world position. We do this by introducing the U model matrix and multiplying it by frag position. The final question is, what is the type of U model? Right now, I put it down as just a float 3x3 or a 3x3 matrix, but we can actually do better than this by making a matrix that goes from model to world. It's parameterized on model and world. And so this informs the compiler that this is a transformation from model to world, and the rest of this code works out. So at this point, we correctly have the reference frame component of our geometry type reasoned about. Unfortunately, there's still a bug in our program. What we expected was an alligator with a light a little bit to the front, and what we got was an alligator with a light to the side. And the reason for this is that the transformation matrix we used cannot handle a certain type of geometric operation. Specifically, a regular transformation matrix can handle rotation and scaling just fine, but it can't handle translation, moving up and down, side to side with our model. What we instead need to be using is an affine transformation matrix. This is very similar to a transformation matrix, but it can also handle translation. So why didn't I just use that in the first place? Well, it turns out it's a little bit more complicated than that. See, because a affine transformation matrix, going back to our idea of coordinate schemes earlier, there are different numerical representations of vectors. You can have Cartesian, spherical, or this very graphics notion of homogeneous coordinates. And it turns out that affine transformation matrices operate on homogeneous coordinates. They require that a vector be represented in homogeneous coordinates before you can operate on that vector. What this looks like in code is that we need to update our reference frame with additional information, what coordinate scheme that reference frame or that object is being represented in. Specifically, light position is in Cartesian coordinates, while fragment position is in Cartesian coordinates as well. On the other hand, UModel operates on homogeneous coordinates. At this point, once again, we get an error where UModel times fragment position. These are different coordinate scheme representations, so we can't apply this multiplication. To fix this, we introduce in GLSL a vec3 of UModel times vec4 of fragment position, comma 1. The reason for the 1 is a bit obscure, but basically we extend fragment position with a 1 on the end of it, multiply by UModel, and then reduce it back to 3 dimensions to end up in to go from Cartesian to homogeneous and then back to Cartesian. Unfortunately, this is a little bit obtuse because it's not clear what we're doing geometrically. It's clear once I described it to you, we're going to homogeneous coordinates and then back to Cartesian, but nowhere does the type system tell you that. So with geometry types, we could do a little bit better and instead use functions, namely hom and reduce, where hom has the type of Cartesian to homogeneous, while reduce has the type homogeneous to Cartesian, thus allowing us to represent what's actually going on rather than having this strange intuition for these functions that don't say what they do. At this point, we've correctly introduced the notion of coordinate schemes as well as reference frames, but we still have one more component. Unfortunately, despite all of our best efforts, there's still one more bug that we have to deal with. See, we expected the alligator to have a nice lighting model, and instead we got this. And this can be very frustrating, especially to a beginner programmer, because it feels like you're really close, but there's something obviously wrong with your model. And what's going wrong is that we're treating points and directions as different things, and each require unique mathematical treatment. So right now we're doing the same operation to our point, our fragment position, and our direction, fragment normal. And what we need to be doing is something different for each of these. Just to remind you, geometric objects, the things we're going to be working with, are things like points, vectors, directions, and even transformations. The thing that actually gets operated on or is represented by our geometric representation, our coordinate scheme in our reference frame. What this looks like in code to introduce geometric objects is we just add the geometric object component, point, direction, and transformation for light position, fragment normal, and UModel respectively. Note that we're working here with frag normal instead of frag position. To update this in GLSL, going back, so first of all, this actually produces an error since we're applying homogeneous to fragment normal. And fragment normal is a direction. Hom cannot be applied to directions. The reason for that is in GLSL, what we needed to do to fix this bug is we need to take this code, vec3 of UModel times vec4 of fragment normal, comma 1, and replace that 1 with a 0. This is very unintuitive and somewhat magical that this is what fixes the issue. But in using geometry types, we can do a little bit better and make this a function instead. We can have reducer and homder, which tell you that you're working on taking you're taking a direction to homogeneous coordinates and then reducing it back to Cartesian coordinates. We can use our type system to inform us of what we're doing geometrically, rather than just adding 1s and 0s and then just hoping the programmer or future readers of the code can figure out what's going on. At this point, by introducing these changes, we have the correct lighting model and we've included all 3 components of our geometry type. However, geometry types can actually do a little bit better than just telling you what errors occur. See, when you want to apply transformation code, say from fragment position to world position, it's a fairly complicated operation that involves several steps. And in raw GLSL, these steps can be somewhat counterintuitive. In Gator, things look a little bit better. In our language, things look a little bit better. You just introduce hom and reduce, respectively, so this tells you what you're doing geometrically, but you can actually do one step better. You can introduce something called automatic transformations or in expressions. You could just say, I want fragment position in world, and it'll figure out automatically the chain of transformations that need to be applied. The reason this is possible is that usually there's only one chain of transformations, one logical way to get between 2 given reference frames or coordinate schemes. So at this point, we've introduced a substantial amount of novelty in the form of both geometric types as well as in expressions, and we would like to evaluate whether or not these can be used in real code. To do this, we implemented a language called Gator and a compiler from Gator to GLSL. And all Gator adds is the novel geometry types as well as in expressions. Using these two new constructions, we were able to write a series of shaders, several of which were shown here: reflection, microfacet, shadow map, and texture, all of which demonstrate a variety of cool features that we were able to implement in the variety of different ideas throughout these shaders, kind of a variety pack of different shader effects. What we also found is that what we also wanted to test, though, is whether or not this is performant, whether or not stuff written in Gator, shaders written in Gator, could perform similar to shaders written in GLSL. And to do that, on the x-axis, we plot the different shaders, and on the y-axis, we plot the frames per second for each of these shaders across a series of experiments. And what this looks like is that the Gator average frames per second in blue is very similar to the GLSL average frames per second for each of the shaders in gray. However, we also performed a statistical test which found that 4 of these shaders were at a 95% confidence had epsilon difference between them. So they were, the differences were incredibly small, even statistically. So what we found is that Gator performs, as expected, very similar to GLSL, despite these mostly compile time additions. Finally, I would like to conclude by reminding you that geometry bugs have been newly identified, and they are a subtle, pervasive, and hard-to-catch type of bug, and that geometry types can rule them out and even generate correct by construction transformation code. Thank you so much for listening. If you have any questions about Gator, feel free to check out the website linked above or email me at dag368@cornell.edu. Of course, you can also ask questions now if you're part of the OOPSLA session. Thank you so much for your time. Have a wonderful day.